Chapter 8, Think and Discuss.
All right, number 101. An automobile speedometer is configured to read speed proportional to the rotational speed of the wheels. If oversized wheels are used, what happens?
If oversized wheels are used, that means the wheel does not have to turn as much in order to go the same distance, and therefore the speedometer should be reading lower values than it actually is. I've had students in the past who had monster tires on their trucks, and they talked about that. Yeah, they learn, when the speedometer says 45 miles per hour, they know they're doing 55 miles per hour or whatever the conversion happens to be. 103, in this chapter, we learned that an object may not be in mechanical equilibrium even if the total force is zero. Discuss what else defines mechanical equilibrium. And this is the point of the Equilibrium 2 lab, that if the total force is zero, that just means it's in linear equilibrium. If the total torque is zero, that means it's in rotational equilibrium. So to be completely in equilibrium or mechanical equilibrium, the total force and the total torque has to be zero. So that means that there's no angular acceleration and there's no linear acceleration. 110, this is a fun one to demonstrate in class because it actually does work. But think about where the pivot point is. The pivot point is not the center of the spool. The pivot point actually is the point of contact between the spool and the ground. Assuming that there's friction there. If you're on a frictionless surface, then the center of the spool would actually be the pivot point and you get a different result. But this is sitting on the ground. So in the middle case, that one was really hard to demonstrate unless you sort of fix it. The middle one, notice that force is directed straight at the pivot point, so there actually should be no torque. As you pull on that, the thing will come up like this, and then it'll start to rotate because once it's in the air, you change the pivot point. But in the first case, I think most people are good with it, that'll roll to the right. But in the third case, it actually will still roll to the right because, again, that pivot point is at the bottom. And so that's my radial vector, because pivot point's down here. My radial vector, my force, and so R cross F is basically going to rotate it this way. 111, we have the obnoxious boy on the seesaw. How is that done? You basically need equal torques on both sides, or roughly equal torques, and you push off the ground and it switches this way, you push off the ground, and so it should be perfectly balanced in terms of torque, much torque on this side as this side. And so because he is so close to the pivot point, he has a very small radial vector there, but the way he's drawn, a little bit more force than the average kid of that age. But on the other side, you have the weight of the board acting down. Well, there's actually weight of the board on both sides, but significantly more on the right side. And so the weight of the board is causing torque. The weight of the boy and the little bit of board is causing torque on the other side, and it balances out because you have a lot more board on the right side, therefore more weight on the right side. So as long as the weight of the board on the right side times the radial vector, which would be from the pivot point to the middle of the board, the middle of the right side of the board, as long as those torques are equal, you should be able to seesaw. 115, when a long-range cannonball is fired towards the equator from the northern latitude, it lands west of the intended longitude. Why is this so? So this is one of those, what some textbooks refer to as a fake force, sometimes referred to as the Coriolis force. And so basically, as I'm shooting down, so I got a globe right here that's rotating. So we'll have it rotate that way. As I'm shooting down this way, it is traveling. The equator is traveling faster than this is traveling in a linear direction because the equator is a bigger bulge. In the same 24 hours, it has to travel this distance, whereas here it only has to travel that distance. So there's a big difference. Coordination. And so when you shoot it, you have less, I guess, latitudinal velocity, latitudinal speed here than you do down here. And so when you shoot it, as it rotates to the east, basically it's still going to move this way, but it won't move. So it's going to basically land right there. 116, we most often say forces cause acceleration, but when Evan took a ride in a rocket sled in Bonneville Salt Flats, blood was forced to the back of his brain, nearly blackened him out. Discuss what happens. Realize there is inertia involved here. So if I accelerate very quickly. There's the blood in my head doesn't want to move. Matter of fact, my whole body doesn't want to move until the whole thing is forced to do it. And blood having, basically the blood wants to stay where it is as the body is forced forward. The blood gets basically, it's not pushed to the back. It stays where it is until the back comes up and pushes on it. And so that's what's happening. It's an inertial property. And that's it.